Welcome back. In this mini lesson we will look at the definition of the so-called cumulative distribution function of a random variable. In the previous mini lesson we defined the probability density function that fully describes a random variable. Nevertheless, it is very practical to have the cumulative distribution function as well, because this function allows us to sample the actual random variable during Monte Carlo simulation. In other words, we want to generate random numbers in such a way that the distribution matches exactly the probability density function of the specific random variable. And the cumulative distribution function allows us to do exactly that. In this mini lesson we will only define the cumulative distribution function, and we are going to learn about how to generate random numbers using this function in one of the next mini lesson. Let's denote the cumulative distribution function by capital F. The function is defined for all possible values of the random variable, and its definition is very simple. The function gives the probability that the random variable takes a value smaller or equal to x. Let's take our example of the distance between two collisions. Let's assume that we know the cumulative distribution function for this random variable, and let's say that we evaluate this function for 5 centimeters. So this value is the probability that the neutron collides within the distance 0 up to 5 centimeters. The cumulative distribution function can be easily calculated for continuous random variables. You just need to integrate the probability density function up to x. The lower limit depends on how the probability density function is defined. If it is defined for non-negative values, then well, you can just integrate it from 0. Some probability density functions are defined also for negative values, so in that case you would integrate from -infinity. The cumulative distribution function is defined in a similar fashion for discrete random variables as well. We can have the example of the reaction type. So we had reaction type number 1 for fission, reaction type number 2 for the capture, and reaction type number 3 for scattering in the previous mini lesson. So in this case, for instance, the cumulative distribution function for the number 2 would give us the probability that the reaction would be either fission or the capture, and it can be easily calculated by summing up the probabilities up to x again, similarly as in the case of the continuous random variables. Let me give you an example of the cumulative distribution function for the discrete random variable at first. Let's take the example of the reaction type, and at first I'm going to redraw the probabilities associated with different reaction types. So we have reaction types here and the probabilities. So the reaction type number 1 was fission, reaction type number 2 was capture, and reaction type number 3 was scattering. And let's just assign the probability 50% to reaction type number 1 and probability 25% to reaction number 2 and 3. I'm going to use the red color now to denote the cumulative distribution function and to separate it from the probability density function, or from the probabilities. Now from the definition it follows that I can actually define the cumulative distribution function even for values for which no probability was assigned. So from the definition it follows that the cumulative distribution function must be 0 up to 1, right? Because we have no reaction type that would have a number smaller than 1. Then for the reaction type number 1, the probability is 50%. So from the definition it follows that the cumulative distribution function is also 50%. Then for the reaction type number 2, we need to combine the probability of reaction number 1 and the reaction number 2 together. So in this case this will give us 0.75. So the cumulative distribution function for the value 2 would be 0.75. So that would be here. So the cumulative distribution function would look like this. And then finally for the value 3, we combine all the probabilities together, and we know that they have to equal to 1. So the cumulative distribution function at the value 3 must be 1. So the cumulative distribution function will look like this, like stairs. Now let's have a look at the continuous random variables. Let's take the example of the distance between two collisions. The probability density function was the exponential function. So let me draw an exponential here. So we have a distance and the cumulative distribution function. Let's assign some value to the distance, for instance 1 and 2 centimeters. And I'm going to use the red color to mark the cumulative distribution function for this random variable. So for instance, for the distance of 0 centimeter, we would need to integrate the function from 0 to 0. So that would give us 0. So the cumulative distribution function for the distance of 0 centimeter would be 0. Let's have a look at another distance, for instance 1 centimeter. So in that case we would integrate the area below this curve over the distance from 0 to 1 centimeter, and we would obtain some value, for instance here. If we wanted to calculate the cumulative distribution function for 2 centimeter, we would then integrate the area from 0 up to 2 centimeter, and we would obtain another value like that. However, calculating the cumulative distribution function this way would not be very practical, because there are infinitely many values for which we would have to calculate the cumulative distribution function value. It's better to calculate the cumulative distribution function analytically, and in this case it is very simple, because we know the equation for the probability density function. The probability density function in this case is the product of the macroscopic cross-section, the total macroscopic cross-section, and the exponential function with the exponent minus sigma t s. Note that the total macroscopic cross-section combines the macroscopic cross-section of all the nuclides in the material. Now let's calculate the cumulative distribution function directly from the definition as the integral of the probability density function from 0 to s. Now this integral is very simple to calculate analytically. The result is 1 minus the exponential function with the exponent minus sigma ts, and it looks like this, right? The maximum value is 1. So that would be all for now, and I will see you in the next mini lesson.